The ratio test. If the limits of the ratio a sub n plus 1 over a sub n at n equal to infinity is strictly less than 1, then the series converges absolutely, so the series without the absolute value also converges. If the limits at n go to infinity of the ratio a sub n plus 1 over a sub n is strictly greater than 1, or if the limit is infinity, then the series diverges. If the limits at n go to infinity of the ratio a sub n plus 1 over a sub n is exactly 1, then the test is inconclusive. No conclusion can be drawn about the convergence or divergence of the series. We must use some other test to determine the conversion or diversion of the series. To justify this, suppose we have the limits that is less than 1. We pick a number r such that r is between L and 1. Since the limits of the ratio is L, there exists a number n such that the ratio is less than r for some n greater than or equal to the capital N. Then a sub n plus 1 is less than r times a sub n. A sub n plus 2 is less than r times a sub n plus 1, which is less than r times a sub n, which is r squared a sub n. And so if we were to look at the infinite sum starting from a sub n, we see that this sum is less than or equal to a sub n plus r a sub n plus r squared a sub n, and so on. And this is the sum of a sub n r to the n at n go from 0 to infinity. We recognize that this is a geometric series, and since the ratio r is less than 1, this series converges. Even though we add up all of the terms from a sub capital N, we see that this series converges, so the sum is finite. If we were to add all of the preceding terms, which is finite, the entire series is still convergent. If L is more than 1, we would perform the same procedures to obtain the geometric series, but since r is more than 1, the series diverges. If L is 1, then we will show by example that the test is inconclusive. If the limits of the ratio a sub n plus 1 over a sub n at n go to infinity is 1, then the ratio test is inconclusive. This simply means that sometimes it is convergent, sometimes it is divergent. For example, the series n squared, where a sub n is n squared, we look at the limits of the ratio a sub n plus 1 over a sub n. We find that the limit is 1. But we know that the series n squared is divergent because the integral of x squared at x go from a to infinity is infinity. The integral is divergent, so the corresponding series diverges. Consider the series 1 over n squared, where a sub n is 1 over n squared. The limits at n go to infinity of the ratio a sub n plus 1 over a sub n is simplifying to the limits at n go to infinity of n squared over the quantity n plus 1 squared, which is 1. But we know that this is a p-series. It is convergent because p equals 2. So diversion and conversion are possible when the limit is 1. And so with the ratio test, if L is 1, the test is inconclusive.